I'm just going to name this section polynomials because we're going to be doing a lot of different things with polynomials. First thing we're going to do is talk about how polynomials are typically written, and then we're going to identify how to name them, and then we're going to look at graphing them and doing some other things today as well. So first up, we talk about what we call standard form of a polynomial. It would be very similar to standard form of like a quadratic equation, because we've already seen that where we do like x squared and then the x and then the constant. But with a polynomial, we're just going to have more terms, and it kind of depends on what type of polynomial we have. So if I were to give you a polynomial that looks like this, and I ask you to put it into standard form, then we always go from the highest to the lowest degree. And the degree is really our exponent. So right now, and a lot of times when they give us our polynomial, it's already going to be in standard form. But if it's not, then that's going to be our first goal. Kind of like when we had a quadratic. We always want that x squared term to be first, because if we have to identify like a, b, and c in order to do the quadratic formula, then if it's not in the right order, then a, b, and c would be mismatched, and then we're going to plug the wrong number into the formula. So if I were to rewrite this one, I would say h of x. My highest exponent is 4, so we're going to put that whole term first, 3x to the 4th. And then we're going to work our way down. Okay, we have x to the 3rd as our next one. And then finally, x squared. And whatever sign is with it, or whatever coefficient is with it, is going to stick with it, and then it would just be minus 5x squared. And that would be what we call the standard form, highest down to the lowest. Okay, when we talk about naming it, I'm just going to go through the first 6, which is 0 through 5. We do have names for each one of these, and some we'll see more than others, and some we've already seen. So if I have a degree of 0, that means I have no variable. It's just a number, like 8 or 11 or something like that, okay? And so if I have a number all by itself, what do we call that number? Does it ever change? It's constant, right? And 8 will always be 8. 11 will always be 11. So we say that it is constant. No variable, okay? There's nothing to plug in for x because there is no variable. So it remains constant. Okay, degree of 1. We spent a lot of time early in the semester talking about equations with a degree of 1. And this is the one we've spent a lot of time with in the past as well. Just our linear function, okay? It's going to make a line. Y equals mx plus b is the one that we spent a lot of time with early on in the semester, graphing at a slope-intercept form, maybe standard form as well, but both of those have degree of 1. Okay, last chapter, we spent a lot of time with a degree of 2. Anything with a degree of 2, we always call it a quadratic. We talked about the quadratic formula, a lot of different ways to solve a quadratic. And so we've seen all 3 of these a lot this year already. Maybe not so much the constants, but linear and quadratics, we've spent a lot of time with those. This chapter, we're going to start getting into some of the higher degrees. But we'll still continue to see linear and quadratic as well, because those are also considered to be polynomials. Okay, 3 is what we call cubic polynomial. The highest exponent is 3. 4 is what we call a quartic. And then 5 is quintic. And those are your prefixes, like quintuplets would be like somebody has 5 kids, which would be kind of crazy, but quintuplets. So degree of 5, an exponent of 5 is quintic. So in this one here, if we were to name this one, then my degree is 4 because it's my highest exponent. So because this one has a degree of 4, we would call this one a quartic polynomial. In the past, you've probably named these by how many terms they have. We don't do that as much in college algebra, where you name it like a monomial, a binomial, and a trinomial. We don't really do that a whole lot. So really, we focus more on the degree and what that degree means than almost anything else, because that degree is going to tell us a lot of information as we go throughout this chapter. So quartic would be this one here. If you go higher than 5, we don't really have any special names for those because we don't see those very often. So if I happen to go to like 6 or 7, we would just call it a 6th degree or 7th degree and so on, and we just use the number to name the degree. Okay, one of the things that we're going to talk about a little bit today is what we call the leading term test. And we're going to talk about this a little bit more as we go throughout the year or the semester to look at a graph and what kind of graph does this tell us. And so from here on out, I'm not going to, instead of writing leading term test every time, I'm just going to write LTT for shorthand because it's quicker. The book probably doesn't use LTT, but I will. And you can do the same thing like on a quiz or a test. And here's what it tells. Basically, it tells us 4 things, okay? First thing that we have to know is what is the leading term? And what is the degree? And we're going to make a little chart here, a little table. Okay, the degree could be even or odd. So if my degree is 2, 4, 6, 8, something like that, then it would be even. If it was 1, 3, 5, 7, it would be odd. And then is my leading term positive or negative? Okay, so let's look at some examples. And some of these we can kind of use some of our previous knowledge to kind of help us with this. So if I were to look at an equation like y equals 3x squared. My exponent is 2, so my degree is 2. 2 is an even number, right? If 3 is positive, what's this graph going to look like? What kind of graph would it be? What kind of shape would it be? Yeah, it'd be a parabola, right? And it's going to open up because it's positive. We saw that a lot in the last chapter. And so I'm just going to draw a real quick sketch of this. All exponents that have an even exponent and have a positive leading coefficient, and it may not be a u always, but each end, we're talking about the leading term, is going to tell us what the end behavior is going to look like. So the end behavior here is going to start up and it's going to finish up. So the 2 ends of the graph will always be going up. If I put a negative in front of the 3, what's that do to our graph? Yeah, it makes it flip upside down, right? And so it's going to go down, down. So if my degree is even, because it's 2, and my leading coefficient is negative, then it's going to start down and it's going to end down. And that's what the leading term test will tell us, is what's the end behavior of the graph. Not necessarily what does the graph look like, but what does the end behavior on the far ends look like. Okay, if we have an odd function, let's just go with one that we're pretty familiar with. Let's say 5x. That's a linear function, right? My degree here is assumed to be 1. 1 is odd. If I graphed 5x, we know that it would be a line, but here's the deal. It has a positive slope, right? So as I draw my line, it's going to start down and it's going to end up. And so my graph is going to look like this. So it starts down and it ends up. If I put a cubic on this one, then it would be like one of those snake-like graphs, and it's going to start down and it's going to end up. And we're going to see a lot of those different types of graphs as we move today. Different types of polynomials today. And then the fourth option in this little chart here is what if we have an odd degree? So here we have a degree of 1 again, but now my leading coefficient is a negative number. So we have a negative 5. So in this case, basically we have a negative slope. So instead of starting down and ending up, it's going to start up and it's going to end down. So it's going to flip-flop my graph. And it's going to look like that. Okay. So you can kind of think about what that means by graphs that we already have done and know, but we're going to see some higher degree polynomials today and some higher degree graphs. And all of these are examples of the end behavior, but then we'll see cubic and quartic and quintic, and we'll have a lot of different graphs that we'll have to do. So if I gave you a function, if I said f of x equals negative 3x cubed minus x plus 4. First of all, the reason we call it the leading term test is the only thing that we look at is the leading term. We don't care about anything else, okay? You might have this big old long polynomial, but all we care about is the leading term. The leading term tells us what this graph is going to look like as far as the end behavior is concerned. My degree here is 3. 3 is an odd number, so it's got to be one of these two, right? My leading coefficient is negative, so odd and negative means it's going to look like this. And that would be my end behavior. It's going to start up and it's going to end down. Now, some people will tell me, well, Mr. Rudo, I'm just going to put that in my calculator. I'm going to see what it looks like, and I'm just going to see, okay, what the end behavior looks like. And that's not a bad option, right? But what you're going to see on some of the graphs like this is the graph's going to be this big old long graph. And maybe you don't see the extremes, the very ends of the graph, because you can't see it in your window. And so then I don't know what the ends of the graph are going to look like. So this is just a really quick and easy way of knowing that this graph is going to start up and end up, or start down and end down, or whatever it's going to be. And we just talk about the direction of the ends of the graph. So a lot of times on these leading term test questions, it might be a graph that you get this big old nasty graph that may not show up exactly right in your calculator. And we'll see that throughout the chapter when we do some of those kind of problems. Okay, another thing that we're going to do today is we're going to evaluate a polynomial. So I'm going to give you a polynomial here. Excuse me. And we're going to do a lot of different things with these polynomials, like graph it and stuff. But this one, all we're going to do is evaluate it. And we're going to see some problems today where we're going to evaluate it. And then they're going to ask us a question. Is this a zero? Okay. Basically, kind of think back to quadratics, right? When we solved a quadratic, we said what values of x would make that equal 0. We would set it equal to 0 and we would solve it. And a lot of times quadratic would have two solutions, right? And so if this is a 0, that means when I plug in a number, does it equal 0? If it equals 0, then we answer it with a yes. If it doesn't, we answer it with a no. Now, I'll show you two ways to do this. One way, and kind of the long way I think, is take each number, plug it in one at a time for x, but we got 3 different x's here, right? And if I have to evaluate it 3 different times, that's going to be a little bit of work. Even though we could still use our calculator to do the work for us, it would still take a while to type that all in. Okay, so I'm going to show you kind of a shortcut to do this. Rather than typing it in 3 different times, or however many times they're wanting us to do it, then a quick and easy way to do this is to put this into your equation. Put it into your y equals. And so that's what we're, these 3. So f of 4, we would say yes. F of 5 is a no, and negative 2 is a no. And we don't necessarily have to show what the value is. You can if you want to. We did that on our table of values. But for this one, we're simply just saying yes or no. Is it a 0 or is it not a 0? Okay, we've talked about standard form. One way that we're going to see some of these equations written is in what we call factored form. And we didn't see this a lot with quadratics. We could have written in factored form in some cases, like x plus 3 squared. Sometimes like when you have it in vertex form, that would be considered the factored form. But in this case here, factored form would look like this. Okay, and a couple of things we're going to talk about here. First of all, they want us to find the zeros. The good thing about factored form is finding the zeros is a piece of cake, because all I have to do is take my factors and set them equal to 0. So those are the 2 places that this graph will cross the x-axis. Those are my zeros. Those are my solutions. Those are your x-intercepts. They're all aligned together, right? Just different ways, different words, different things that we say about them, but they all mean the same thing. Those are our solutions of this equation. Okay? There is no reason for you to do a bunch of multiplication and multiply this out and put it in standard form. Okay? That would be way too much work. We're not going to do all that. Plus, in the factored form makes this a whole lot easier. Okay? Now, a different thing that we're going to talk about here is what we call the multiplicity. Hey, the multiplicity is based off of the degree. And what this one is it's a little bit hard, right? But we're going to look at the degree of each one individually. So in this case here, x plus 3 happens 2 times, okay? And so if it is even, then this is not really a mathematical word, but I'm going to use the word bounce, okay? So here I'm going to say that this one has a multiplicity of 2. And I'm going to show you what the graph looks like here in just a second, so you can understand what I mean by bounce. We kind of talked about it with quadratics just a little bit. If it is odd, it's going to go through the x-axis. This one has a degree of 1, so it has a multiplicity of 1. Okay, so in this case, they might just be asking us what the multiplicity is, but I'm taking it a step further, and we're talking about what does the graph do as well. Okay, because I think that's going to be really, really important to know and understand. So this one has a degree of 2, a multiplicity of 2. This one has a degree of 1, so we say that it has a multiplicity of 1. Okay, because this one is even, it's going to bounce at -3, and it's going to go through the x-axis at -1. So I want to show you what that looks like. And you guys can put this into your calculator as well if you want to. When you talk about multiplicity, they're just asking you what the multiplicity is. All that means is x plus 3 happens 2 times. Okay, so it has a degree of 2. multiplicity of 2. Okay, this one here would be even bigger. And once again, we're not going to multiply all this out, but I just wanted you to see one like this. We're going to set each one of those factors equal to 0. This is factored form once again. We have 4 different factors. There is no plus or minus sign attached with this x. So it's just x. X equals 0. X plus 3 equals 0. X minus 1 equals 0. And x plus 1 equals 0. We set all of those equal to 0. We're going to solve all of them. The first one's already solved. The rest of these are pretty easy to solve. They're just one-step equations. So if we were to graph this, I'm not going to graph this one. If you really wanted to, you could. You could put this whole thing into your calculator and you could see where it touches the x-axis at. But these would be the 4 places that it's going to cross the x-axis or touch the x-axis. Okay? My multiplicity for these, this one has a multiplicity of 2 because my exponent is 2. It's that simple. Okay? For the next one, has a multiplicity of 2. If there is no exponent there, then it's assumed to be a 1. So we would say it has a multiplicity of 1. And finally, the last one has a multiplicity of 4. That's all you're doing. Okay? So if it's in factored form, finding the multiplicity and finding the zeros, really pretty simple. Okay? You're just setting it equal to 0 and solving it. Okay, this one's a little bit harder, okay? It's not in factored form. This one is back to standard form. Hey, thanks.
I don't see Maddie.
Maddie's not here. You just want me to hang on to it?
Yeah.
Okay.
Thank you.
So here the directions are the same as what we did on the last one, except it's going to be a little bit more work to find what we're going to do. Okay? Now, I'm going to show you a method that we're going to do here that we actually did last chapter, and it looks a little bit different here because we have x to the 4th. We didn't see any x to the 4ths in the last chapter. But we're going to do a factoring method that we did do, and because we have a trinomial here, we're going to factor this just like we would factor any other trinomial, just like it was x squared. We're going to use the product and the sum method here. And so we're going to look at this and we're going to say, what multiplies to get 3 and adds to get negative 4? Okay? So I'm going to do my 2 sets of parentheses. Now here's where it's different. When this was x squared, we did x times x, right? Because this is x to the 4th, the first term in each parenthesis would instead be x squared and x squared. Because x squared times x squared becomes x to the 4th. So that's really the big difference here. Everything else is really the same. And it doesn't matter which one you put first, negative 1 or negative 3. Those are my 2 factors. But we got to solve, right? So now to solve this, and this is where it goes back to last chapter, we had a problem on the test yesterday that was similar to this. I think the one on the test had an I in it. This one doesn't have any I's in it. But this is the square root method. Whenever we do the square root method, we got to put plus or minus on our answers. And then same thing here. Okay, one thing that I'm going to point out here, and I'm going to show you this graph so you understand what's going on a little bit. We have a degree of 4, which means we have 4 zeros that we have to account for in some shape or form, okay? And that's one thing that we're going to continue to talk a lot about, okay? So we have to have 4 zeros. That's why the plus or minus is critical here. Also, the directions here are find exact zeros, kind of like we saw yesterday on the test. When it said exact zeros, we don't want decimals as our answer, right? Especially if it's a big rounded decimal. And that's why I could put this into my calculator right from the start. I just want to show you. Bless you. They all have multiplicity 1. They all happen one time because the graph goes through at that place. All 4 are 4 different zeros. So we have 4 different zeros for a degree of 4. Okay? And so they all happen one time. And that would be our multiplicity. Okay? Questions on that? Okay. Another type of factoring that we did a little bit with. And they threw one of these at us in chapter 2, and I told you that it was kind of like out of it was kind of misplaced, I thought. Because we didn't talk about any of the grouping ones. And that's because it was a polynomial that was bigger than x squared. And we only talked about x squared in that chapter and then or in that section, and all of a sudden they threw one of these in. So if I give you this, okay, we can't do product and sum, we can't do slide and divide, we can't do any of those because this is a cubic polynomial, okay? And so we have to do the grouping method. And I showed you one of these in the last chapter, but when we talk about grouping, we're going to split this up into 2 groups of 2. And then we do GCF of each group. So out of the first group, what could I take out? X squared. And that would leave me x minus 2. Out of the second group, what could I take out? 9. Okay, and here's what we're going to do. We want our 2 parentheses to be the same. So not only are we going to take out 9, but I'm going to take out a negative 9. So negative 9x divided by a negative 9 would make that a positive x. And then 18 divided by negative 9 would be negative 2. And what we want to happen is we want those 2 parentheses to be the same. If those 2 parentheses are not the same, then grouping is not going to work, okay? And we'll see this off and on throughout the chapter. So it has to be the same, okay? Non-negotiable, x minus 2 have to be the same parenthesis. That's why we want to force them to be the same if we can, which they are, okay? And then we're going to combine the outside parts together to be one of our factors. And we're going to leave the inside part as our other factor. Well, what could we do with x squared minus 9? What kind of factoring can we apply to x squared minus 9? Stops, you bet. Okay, so there's another factoring method. And so we would do x plus 3, x minus 3, and x minus 2. Okay? And those are my 3 factors. My 3 zeros here would be negative 3, positive 3, and 2. if I graph this, and I'm just, for the sake of saving time, I'm not gonna graph this, but if you wanted to graph this, this would be the three places that it's gonna cross the x-axis, okay? And because we have a degree of 3 and we have 3 different zeros, then once again, they all have a multiplicity of 1. Okay, they all happen one time. They're all gonna go through the x-axis at that point. Okay, another thing that they're going to throw at us today and we've already talked about this a little bit, is what is the relative min and max? Okay, the relative min and max is where the graph reaches a high point and a low point in the graph. When we did a parabola, it was one or the other, right? Because the graph was either going to open up or it's going to open down. And so if it opens up, it's going to have a minimum. If it opens down, it's going to have a maximum. So when we did parabolas, we said one or the other. Here, we're going to see that has both, okay? And in most cases. So if we just said, what is the relative max? And what is the relative min? We're going to see a lot of these that have both a minimum and a maximum. So let's graph this one. That's the best, easiest way to find the relative min and max. This one has a maximum of 14, and that happens at x equals -3. And then we do the same thing for the minimum. X equals 1. And that would be our two minimums and maximums. Okay, the last thing I'm going to throw at you today is another solving one. If I ask you to solve this equation, it's a quartic equation, and we kind of did one like this just a little bit ago. It's a trinomial, okay? So anytime it's a trinomial, I can do the same thing as I did with like quadratics. And so if I ask you to factor this, once again, we could do product and sum, right? And I could say this is my product, this is my sum. X squared times x squared is x to the 4th. Okay, what multiplies to get a -45 and adds to get a +4? 9, okay. +9, -5. Those are my two factors from that, but now we're going to solve both of those. Okay, this one looks like DOPS, but it's not DOPS, okay? Because DOPS has to have a subtraction sign here. So be careful here, right? It's not x squared minus 9, it's x squared plus 9. So here's what we have to do. We have to set both of these equal to 0 individually. And when I take the square root of -9, what would be my solutions there? What happens when I take the square root of -9? 3i, good. And because we're doing the square root method, we got to put plus or minus on it. Over here, I'm going to add 5. And those would be my four zeros, my 4 solutions. 2 of them happen to be imaginary, 2 of them happen to be a radical. Okay, so we have a situation here where we have no nice integer zeros for our graph. So just something we're going to see once again a lot as we go through this chapter. So something I wanted you guys to see there.